In this video, we're going to look at another example of areas between curves. In the question here, we have find the area of a region bounded by the curves y equals e to the 1 minus x, y equals e to the x, and between x equals 0 and x equals 1. The first step, as always, is to find the intersection points of these two functions. Y equals e to the 1 minus x, and y equals e to the x. And we do that by letting y equals y. So we will get e to the 1 minus x is equal to e to the x. Now let's log both sides, and what we get is log of e to the 1 minus x is equal to log of e to the x. Now log and e, they cancel out because that's the rule here. Log of e to the x is equal to x, and e to the log x is equal to x. So we get 1 minus x on the left-hand side, and right-hand side, log of e to the x is just x. Solving for x, put all the x's on one side, we get 2x is equal to 1. And divide by 2, we get x equals 1/2. We can plug it into either equation. I'll just put it into y equals e to the x. And we get y is equal to e to the 1/2. This is the intersection point, 1/2, comma, e to the 1/2, xy coordinates. All right, the next step is to sketch the bounded region. We have y equals e to the 1 minus x, y equals e to the x, x equals 0, x equals 1, and we have sketched it here. You should be able to sketch these. E to the x is your basic exponential function that has a y-intercept of 1. It has a horizontal asymptote x-axis as x goes to minus infinity, and when x goes to infinity, y goes to infinity, and that's why it's called exponential growth. All right, so notice when x is less than 1/2, larger than 0, that e to the 1 minus x is larger than e to the x. So the top point of contact, which is e to the 1 minus x, this y value, is larger than the bottom point of contact, which is e to the x. So therefore, the differential area, dA, is equal to y top minus y bottom, e to the 1 minus x minus e to the x times dx. Now we also notice when x is less than 1, larger than 1/2, now e to the x is a top function. E to the x is larger than e to the 1 minus x. The top point of contact here is e to the x when x is larger than 1/2, when x is between 1/2 and 1, and the bottom function is e to the 1 minus x. So what we have is the differential area dA is equal to e to the x minus e to the 1 minus x dx. Let's draw a typical rectangle for this region as well. So here's a typical rectangle. The height is going to be e to the x minus e to the 1 minus x, and the width is dx, and this is a differential area. This shaded region is a differential area. All right, so we're now going to set up a definite integral to find the area, and then we're going to solve this integral. The point of intersection, as we found already, is x equals 1/2, and y equals e to the 1/2, on the interval x between 1 and 0. And we also showed that e to the 1 minus x is larger than e to the x when x is between 1/2 and 0, and e to the x is bigger than e to the 1 minus x when x is between 1 and 1/2. So we have to set up two separate definite integrals to describe these two regions and add them up. So the definite integral that represents the area is going to be area is equal to integral from 0 to 1/2 e to the 1 minus x minus e to the x dx plus 1/2 to 1 e to the x minus e to the 1 minus x dx. So always this is y top minus y bottom. It's always more minus less. And that when we do that, we get a positive quantity. We're adding up positive quantities. So if your integral comes out negative, it means a mistake took place. So always you should have a positive quantity for these definite integrals. And here we have y top minus y bottom. All right, so now we have to solve these integrals. The hard part of this integral is e to the 1 minus x, so we're going to apply U substitution. We'll do that first. We have e to the 1 minus x dx. Well, it's not really that hard. It's kind of easy. It's just a regular U substitution. We're going to let u be the exponent, which is the inside of the exponential function. U is equal to 1 minus x. Differentiate both sides. We get du is equal to minus dx. So we get integral e to the u, and dx is du minus du. I'll put the minus outside. We get minus integral of e to the u is itself e to the u plus c. Now put u back in. We get minus e to the 1 minus x plus c. All right, so let's do the integration. The area is going to be integral of e to the 1 minus x. We just showed using u substitution. That's going to give us minus e to the 1 minus x. Integral of e to the x is just e to the x, evaluated from 0 to 1/2, plus integral of e to the x is just e to the x, minus, and integral of e to the 1 minus x is minus e to the 1 minus x, evaluated from 1/2 to 1. So now we get area is equal to minus e to the, let's put the upper limit in, 1 minus 1/2 is 1/2, minus e to the 1/2, minus, put a lower limit in, we get 1 minus 0, that's the exponent, that's 1, we get minus e to the 1, minus e to the 0, close the bracket, plus, put the upper limit in, we get e to the 1, minus minus is plus, e to the 1 minus 1 is 0, minus, put a lower limit in, we get e to the 1/2, plus, let's just make that a plus, e to the 1 minus 1/2 is 1/2, close the bracket, another close, and now let's simplify. Area is equal to, so what we have is minus e to the 1/2 minus e to the 1/2, that's minus 2 e to the 1/2. E to the 0, of course, is 1, so we get minus, minus minus is plus e, and minus 1 is plus 1, plus e, plus e to the 0 is just 1, minus, and then e to the 1/2 plus e to the 1/2 is going to be 2e to the 1/2. We simplify this very, very carefully because it's easy to make mistakes. Minus 2e to the 1/2 minus 2e to the 1/2, that's going to give us minus 4e to the 1/2, plus e is 2e, 1 plus 1 is 2. And if we decimalize this, we get an approximation, 0.842. This represents the area bounded. Let's show that on the graph. So the area bounded is given by 0.842, and that's the green shaded region. All right, thank you.